right, so the lesson today is talking about the mole and mole conversions. So our learning objective, I can describe how a mole is used in chemistry and relate the mass of one atom to the mass of a mole of atoms and identify proper units of measure for each. We will also be working through some math examples at the end of this lesson. All right, so our first question is, why do we use counting units in chemistry? A counting unit is a word that stands for a specific number of things. You know some examples of counting units. So if you think of a pair of shoes, right, that's going to be 2. Or if you look at those donuts, which look awesome, we know that a dozen is going to be equal to the number 12. So this is just a simpler way to talk about a number. So I can say like a pair of shoes or a dozen donuts or flowers. And everyone kind of already knows that like it's 2 and it's 12. In chemistry, we're going to use counting units to make it easier to keep track of big items or small items with normal numbers. Let me explain that for a second. So a question I would pose is, would it make sense to measure how far a car drives in inches? If you think about it for a second, you're probably going to say no. Well, why not? If I drove from my house to Eisenhower High School, I would be driving a whole lot of inches, and it just doesn't make sense to measure that large distance in inches, and therefore we measure it in miles. So it's just an easier way when we're keeping track of different measurements. So in chemistry, with counting atoms and molecules, remember that atoms and molecules are so small. It would take forever to count how many there are. So we need to have a bigger unit to account for all of those tiny particles. Now in lab, we're not going to be measuring individual carbon atoms or individual carbon dioxide molecules. We're going to be measuring larger quantities of these things. Therefore, we're going to need a simplified unit to help us keep track of how much the material we have. So this simplified unit is called a mole. So you may think of a mole just from prior knowledge as a skin feature, right? Or a furry, really nasty looking rodent. But a chemist thinks of the best counting unit of all time because they're going to use it all the time. So with a mole, it is going to be equal to 6.02 times 10 to the 23rd particles. Now that is a huge number. 6.02 times 10 to the 23rd is, let's see, 1, 2, 3, 4, 5, 6, 7. That big. It is a huge number. If we had to type all those numbers into a calculator or even write them down, it's just more chance that we're going to have an error. All right, so that 1 mole that's equal to 6.02 times 10 to the 23rd particles, those particles can represent molecules, they can represent atoms, or they can represent formula units, and we'll get into that a little later. So just how big, if we really want to quantify how big this number is and put it into something that we can maybe try to relate to, you can say that a mole, so if I had 6.02 times 10 to the 23rd marshmallows, would cover the Earth, so it would go around the whole Earth 12 miles high. Now, I don't know about you, but 12 miles to me is a very long distance, especially when I'm running or walking. If I can't even imagine a mole of marshmallows 12 miles high from the Earth, it is a huge number. So recall that I said that chemists really need this simplified unit to help them make sense of the measurements that they're taking. So scientists need a way to convert between the number of particles and the measurements used in the lab. And the number, the 6.02 times 10 to the 23rd, is also known as Avogadro's number. This number is experimentally derived using data. and chemists are able to link a mole of atoms to an important mass value based on the atom's atomic structure, the atomic mass unit. Now keep in mind, remember when we were calculating AMUs back in first semester? That is going to include protons and neutrons. And all that mass was going to be located within the nucleus. So researchers found that one carbon atom, as we know, is equal to 12 atomic mass units. And that is due to the 6 protons and then the 6 neutrons. Now at this point, the researchers knew the approximate masses of one proton and one neutron. So they took 12 grams of carbon and basically divided it by the number of protons and neutrons to get that 1 mole of carbon atoms, which was equal to the 6.02 times 10 to the 23 atoms of carbon. They did the same thing with other elements. So they took oxygen, they took nitrogen, they took sulfur, and they realized that when you took the atomic mass unit, it was actually going to be equal to the molar mass of that 6.02 times 10 to the 23rd atoms of the substance. So when we're calculating the atomic weight or the molecular weight, this is when we're using those AMU units. So that's going to account for basically the one atom. So what I'm going to do is just look at the atomic mass that is on my periodic table. So if you look at your periodic table, you'll see that a carbon is going to be 12.01 AMU. Oxygen, 16.00 AMU. For a compound, remember that we have to add all of the atoms in that compound. So carbon would be 12.01, and each oxygen, should probably get rid of that, is going to be 16.00. All right, so you should get 44.01 AMU for carbon dioxide. And you can do the same thing for the next two. I'm not going to do those for you, but I would highly recommend you do those on your sheet. As I said, scientists found out the relationship between atomic weight and molar mass. So the molar mass was going to be equal to 1 mole, or 6.02 times 10 to the 23rd atoms or molecules of the substance. So carbon is going to be 12.01, just like it was for the atomic weight. The only difference is that you are going to measure molar mass in grams, because mass is what we measure with grams. So it's going to be 12.01 grams. Oxygen would be 16.00 grams. Carbon dioxide would be 44.01 grams, and so on and so forth. So atomic weight is going to equal the same for molar mass. The only difference is that we are measuring in grams. And with atomic weight, we're really measuring the weight of the one atom, whereas the molar mass, we are going to be measuring the mass of a mole of the particles. All right, so you're probably wondering, what does this mole have to do with converting units? So we already talked about 2 different conversion factors that involve the mole. The first one dealt with a counted number, and the second one dealt with the measurement. So these conversion factors are going to allow us to convert between the quantities when we're working in the lab. When we're talking about the counting number, remember we could count particles. So the counted number, the number of particles or atoms or molecules or formula units, is going to be 6.02 times 10 to the 23rd, and that's going to be equal to a mole. So these particles, as I mentioned before, could be atoms, so something like magnesium atoms, copper atoms, carbon atoms. Those are single elements. Molecules which would be something like H2O. Remember, these are covalently bonded to one another. CO2, also those diatomic elements, so something like oxygen or nitrogen, those are molecules when they are diatomic and bonded to each other. And then formula units, which are representing our ionic compounds, so something like NaCl or K2O, potassium oxide. So these formula units, remember, are basically simplifying the lowest ratio of the cation to the anion. So it's going to be the lowest ratio of cation to anion, and that's what we write as our formula in our formula unit. Now, the reason that they're called a formula unit is because usually these ionic substances are going to be crystal, and it's just going to be a repeating pattern. So you always want to find like the lowest ratio to get what that formula unit is. The other conversion that we talked about is going to be our molar mass conversion. So we said that 1 mole of a substance is going to be equal to the molar mass of that substance. So keep in mind, molar mass is going to be equal to the atomic mass, but instead of AMUs, it's going to be reported in grams. So molar mass is always going to be reported in grams. So think of this as a measurement versus counting. All right, something else to discern between these two things is that when you have a mole of anything, it will always be 6.02 times 10 to the 23rd. So a mole of anything is always 6.02 times 10 to the 23rd. Doesn't matter if it's atoms, molecules, formula units, or silly things like dogs and cats. A mole is 6.02 times 10 to the 23rd. With molar mass, this is going to change depending on our substance. So the molar mass of carbon dioxide is not the same as the molar mass of water or of hydrogen gas. All right, so for our first example, it's asking how many moles are in 19.4 grams of oxygen gas. So the first thing that I'm going to see is it's asking me how many moles. Okay, so moles is going to be my wanted unit. So I want to convert to moles. They're giving me that I have 19.4 grams of oxygen here. So this is what I call my given. All right, so I'm always going to put the given in the upper left-hand corner of my dimensional analysis grid. So I would put my 19.4 grams of oxygen gas, which is O2, molecular oxygen. Remember, oxygen is one of those diatomic elements, so it's never going to really exist by itself. So 19.4 grams of O2. Now, remember that we had two choices. We had the counting choice, or we had the mass measurement choice. And both of those are going to be equal to 1 mole of the substance. All right, so here I'm given grams in my given. Therefore, that tells me that I really want to use this mass measurement. So what I have to do is find what is my molar mass for oxygen, because I know that the molar mass is equal to 1 mole of oxygen. So my molar mass for O2, all right, I have oxygen, and I have 2 of them. So I have 2 times, so that's my 2 oxygens, times the atomic mass unit of oxygen, which was 16.00. So that gives me 32 grams per 1 mole of oxygen. Now, it's really important that when you are doing dimensional analysis with moles, and we're going to move into stoichiometry later, that you're always going to have a unit and a label. So your unit is going to tell you what kind of measurement it is. The label is going to tell you what the particle is. So here I can cross out my grams of oxygen, all right, and I'm going to be left with moles of oxygen, which is what I'm solving for. All right, keep in mind you're going to multiply the top and divide by the bottom. All right, so when I plug this into my calculator, I would type in 19.4 times 1 divided by 32, and I get 0.606, and my unit that I have left is moles of oxygen. Notice that when I write the abbreviation for the unit mole, it's just MOL. I know it doesn't cut off a lot for that abbreviation, but when you are writing this in dimensional analysis or the factor label method, you should really be using that abbreviation for mole. So MOL is the same thing as mole. It's the symbol for mole. Okay, so example number 2 says to determine the moles of 5.67 times 10 to the 14th atoms of carbon. So here, right away, that number kind of sticks out to me and tells me that this is going to be my given. So this is what's given to me in the problem, and determine the moles means that I am solving for moles. So this is going to be my wanted. All right, when I set up dimensional analysis, I'm always going to put my given in the upper left-hand corner. From here now, I have to decide which conversion factor I'm going to use. So remember that there's the counting conversion factor and there's the measuring conversion factor. Well, here it's talking about a number of atoms. So therefore, that tells me I'm going to use the one that was counting. So remember that 1 mole of anything is going to be 6.02 times 10 to the 23rd. And in this case, we're going to do atoms of carbon. All right, so in order to cancel out atoms of carbon, I already have it in the top is my given. Therefore, this part is going to have to go on the bottom so that my atoms of carbon cancel. And that means that 1 mole of carbon will be up top. All right, so once again, notice how I am using my units and my labels. All right, this is going to be really important, especially when we get to going from one substance to another in dimensional analysis. So please just get in the habit. You should have a unit and a label of the substance. All right, so when I punch this into my calculator, all right, so just a trick, if you're not familiar with how your calculator works, you're going to want to get familiar with it. So you can either use the caret symbol, or there might be a button on your calculator that says EE. If you use EE, this replaces the times 10 part. So if I wanted to put 6.02 times 10 to the 23rd in my calculator with that EE button, I would just simply hit 6.02 EE, so that's a button, 23. And that would give me the 6.02 times 10 to the 23rd. If you use a caret, you just have to be careful because you're going to have to put your numbers in parentheses. So if I have 6.02 times 10 and then the caret 23, just make sure that that's all in parentheses so that your calculator is doing it correctly. So when I typed this into my calculator, I got 9.42 times 10 to the negative 10. And then the units that I'm left with are going to be moles of carbon. All right, so for this last one, it's asking us to calculate the number of molecules present in 6.85 grams of C3H5O4. All right, so once again, that number really sticks out to me. All right, that tells me that I have 6.85 grams, and this is going to be my given. And then it's asking me to calculate the number of molecules present in that amount of C3H5O4. So this is going to be my wanted unit. All right, so once again, we're always going to stick our given up in the left-hand corner. So 6.85 grams C3H5O4. Notice how I put my unit and my label here. Okay, so here's the tricky part. I have grams, and I only have two options to use for my conversions. I have, remember, the counting mole conversion or the measuring mole conversion. With the counting mole conversion, remember it was 1 mole is equal to 6.02 times 10 to the 23rd, and this time we'll use molecules. The measuring was our molar mass. So we're not given the molar mass here, we would actually have to calculate it, which we already know how to do. So I know that 1 mole of C3H5O4, if I add all those atoms up, let's see, I have 3 times 12.01. I'm going to add that to 5 times 1.008. And then I'm going to add that to 4 times 16.00. So keep in mind I got these numbers from our periodic table, those atomic mass units that you see on there. When I add this all up, I got that 1 mole is going to be equal to 105.07 grams of C3H5O4. Okay, so these are really the two conversions that I can use in this problem. So here I'm given grams. If I look at these two conversions, there is only one that includes grams that I would be able to cancel out, and it would be this measuring one. So I'm going to use that one first, and I want to cancel out my grams. So if I have grams on the top right now, I'm going to have to put my other grams on the bottom. We know that's equal to 1 mole of C3H5O4. All right, so right now, if I cancel out my units, it's a 0. I have moles of C3H5O4. Now, the problem didn't ask me how many moles are present, it asked me how many molecules. So now I'm actually going to also use my counting conversion. All right, so I want to cancel out moles and I want to get to molecules. So in order to cancel out the moles, it has to go in the bottom. And then my molecules would have to go on the top. All right, so if I typed this into my calculator, I would do 6.85 times 1 times 6.02 times 10 to the 23, so depending on if you're using the caret or the EE button, and then divided by 105.07 divided by 1. All right, and when I do that, what I get is 3.92 times 10 to the 22nd, and that would be, I didn't put that here, molecules of C3H5O4. And I mistakenly didn't put this here, but always look up here at your conversion factor, and we said 1 mole was going to be equal to molecules, and that is the unit that we have left, and that is what we're solving for, so everything checks out. All right, so you're going to be doing some extra practice with this. You're going to do a simulation that'll kind of take you through on our CK12 website that we're going to start using. And then you're also going to have a practice sheet where you're practicing calculating molar mass and then also practicing going from grams to moles and moles to grams. We might throw in some of these molecule ones, just not sure how familiar you guys are with using exponents and scientific notation. So we're gonna kind of see how that one goes. Maybe we'll put it on an assessment and then not count it. I kind of just wanna see how you do on it. All right, if you have any questions, make sure that you come to my office hours. I am available for video chat or by email. I can pretty much tell you anything you need to know by email, but if you wanted to video chat, if you want me to show you something, I am more than willing to do that. Just let me know and make sure that you guys are staying on top of doing your work and asking questions whenever you need to.